Hello everybody, this is Tommy and welcome back to the last weekly Physics Explainer videos. This is going to be the last in the series. I know many of my fans out there are going to be very sad, but this is it. This is the last problem, and the prompt for this one was just create some kind of amalgamation of physics concepts and just jam them all into one problem, as many as you can, as many chapters as you can into a single problem. So I've just gone ahead and drawn all this beautiful stuff here in MS Paint. So first of all, some important assumptions about this problem. This is going to be taking place on, I don't know, some planet Z. Things are going to be a lot different here, like the mass of the planet, and maybe like the radius of the planet, and maybe like good animated movies on this planet won't have a crappy like live action sequel. The ones that nobody asked for. You know, but that's besides the point. But I just want to make the point that things are different on this planet. So like things like the gravitational constant G, we don't know none of that. So we're gonna need to calculate it. But first, let me explain the mechanisms that this contraption, not this contraption that I've drawn here. So this is going to be a button with an arrow pointing to the button for some reason. I don't know why, but there's just an arrow pointing to it. So this button is going to be connected to some kind of mechanism that's keeping a spring compressed, and on top of that spring, there's going to be an ice cube. And once this button is pressed, the spring will launch this ice cube into a pool of water right here. And after it has been launched, I don't know, stuff. So, but let's just get back to the initial like pressing of the button. So, after we press the button, the spring is gonna decompress, and it's gonna launch this ice cube, and it's also gonna like I don't know. It's also gonna like oscillate or something. Like maybe we could just find the period using the formula for the to find the period of a spring. Just 2 multiplied by pi multiplied by the square root of the spring constant over the mass of the spring. Just for fun. Maybe we're some kind of physics geek and we just want to calculate stuff. And say that after the spring launches the ice cube, we want to calculate the range. Maybe we don't. Maybe we're not sure if it can reach it or not, and we just want to calculate the range of our launch. So that's going to be the velocity, because for some reason we know the velocity of the ice cube after it launches from the spring, and the multiplied by sine 2 theta. You also just know the angle of the launch for some reason. I guess you also just measured that. I don't know how, but you measured it. And but what's this? We're gonna need G. But didn't I say that G was gonna be different on this planet? That's right. It is gonna be different because the planet has a different mass and a different radius. So we're gonna need to calculate it. Why would we need to calculate it? You say? I don't know. Maybe you forgot the gravitational constant for this planet, and the only computer you have to search it up on is a crappy Windows 10 or not Windows 10 Windows XP computer that like takes like 10 minutes to boot up, and you decided that, hey, I just have the mass of the planet and the radius just lying around somewhere, and I can just calculate it, and that's going to be faster than booting up a Windows XP computer. So yeah, you just calculate it, and then you can use that to get the range of the ice cube, and then after the ice cube has been launched, say we just feel like doing more calculations. We've already done a bunch of calculations, so why not just do some more? We could also calculate like the buoyancy force of the water once it's just floating in the or the buoyancy force of the ice cube, not the water. Once it's just floating in the water, and it's going to be the density of the water multiplied by the volume of the water that's displaced multiplied by that gravitational constant G that we just calculated. And once the ice cube is going to be in that water, it's going to start melting. So we're going to need to. I don't even know why I say need. We don't really need to do this, but I don't know, I guess we just really like calculating things. We can say if we have like the initial temperature of the ice cube and the water, and then we take the final temperature of the system after the ice cube has melted into the water, and we could try to calculate. Also, you also know the mass of the ice cube. You just calculated a lot of these things beforehand because you really like physics for some reason, I guess. So it's gonna be the heat energy is gonna be equal to the mass multiplied by some constant and then the change in temperature. So you can multiply that either way. It's like the mass of the ice cube multiplied by this c right here, and then the change in temperature. You just find the you just take the final temperature and minus the previous temperature, and then you get the change in energy, and that's pretty cool, I guess. But then, oh no, say that after you've put the ice cube down, or not put the ice cube down, you've launched the ice cube into the water. I don't know, your mom gets like hit by some of the water. She gets like splashed by it, and then she gets like angry at you, and then she starts I don't know, like, yelling or something, and then now you see these approaching sound waves, and before your eardrums rupture from the sheer force of your mom screaming at you, you know that you need to pull out the noise canceling headphones from that one week 5 explainer video, where it just basically output the sound except with a delay, and that delay was the 1/2 of the period of the sound wave. So that's gonna be 1 over the frequency, and then you can use that to program the headphones. And why would you know the frequency of your mom's voice? I don't know, maybe she's yelled at you so much, just instinct, and you just know the exact frequency. So these two waves, this is like the sound wave and the one generated by the headphones, they're going to destructively interfere with each other, so you just get some nice peace and quiet. And yeah, that's the entire problem. So that's like Newton's gravity. That's like 5 of them. Like Newton's gravity, and then there's like there's some oscillation, there's some fluids, like the buoyancy force, and there's like some heat exchange, and then there's like waves. So yeah, that's like 5 stuff. This is gonna be the last one, so goodbye forever. Also, I just looked at the recording without realizing. So yeah, this is what I used to record the entire quarter. So I guess everybody knows now that I use OBS. Well, goodbye.